Hello everyone, welcome to Module 3 of your Chem 1 laboratory. I am Ms. Angela Joy Lozano and I will be discussing about the different types of chemical reactions and solutions as part of your pre-laboratory. Our objectives for this module is to differentiate the different types of chemical reactions and observe the changes that occur. Included in our objectives is that we need to be familiar with the properties of solutions and the factors affecting solubility. Now start with a discussion of chemical reactions. So let's define first what a chemical reaction is. Chemical reaction is a process in which at least one new substance is produced as a result of a chemical change. So when you are doing an experiment, most of the times we are observing chemical changes, and this is because of the different chemical reactions that occur between two new substances. As stated in this definition, there is at least one new substance that is produced. In chemical reactions, there are two components involved. We have the reactants and the products. The reactants, these are the primary chemicals or substances that you interact with each other to produce products. Products are the end result of your experiment or the chemical reaction. So how does a chemical reaction happen? Chemical bonds between the atoms break in the reactants and new bonds form in the product. We have an example here, hydrogen and oxygen will produce water. So hydrogen and oxygen are our reactants and our product is water. If you are to observe the chemical bonds in our reactants, as stated in this definition, they break. Okay? So bonds in the reactants break, and then new chemical bonds form in the product. So upon undergoing chemical change or upon undergoing chemical reaction, bonds break, atoms rearrange themselves, and they form new chemical bonds, just like this bond between oxygen and hydrogen to produce atom or to produce water molecule. There are different evidences of chemical change that we can observe to see if a chemical reaction really occurred between the two substances that we are observing. First, there should be color change. There could be a precipitate, gas and heat, and there could be a odor change. Here are some of the examples. Let's take a look at them. Here are some of the examples. Let's try to take a deeper look at them. First we have is the color change. And as you can see, upon adding the purple substance, you can see that there is a color change in our product, indicating that there is a chemical change or chemical reaction that occurred. Another thing is precipitate or the formation of precipitate, wherein we are referring to the precipitate as the solid or insoluble substance in the solution or in the chemical given. Then we also have the production of heat. This can be in form of fire, flame, sparks, or it can even be just a simple change in temperature. We also have the formation of gas, which is observable by the existence of bubbles, effervescence, or smoke. And we can also observe for the odor change in a specific substance. Let's say, for example, as seen in the picture, a rotten egg. As time passes by, chemical change occurs in a rotten egg, causing it to emit a pungent or foul-smelling odor. Now let's proceed to the different types of chemical reactions. We'll be discussing 5 different types of chemical reaction. First, we will be discussing combination or synthesis, decomposition, single replacement, double replacement, and combustion. We'll be discussing their definition and how you can observe them in a chemical equation. First, we have the combination or synthesis reaction. This is when a single product is produced from two or more reactants. So what is the formula for combination reaction? So for the combination reaction, it says here a single product is produced from two or more reactants. So it can be written simply as A plus B will produce AB, wherein A and B are your reactants and they will simply combine with each other or bond with each other to produce your product. We have to remember that in a combination reaction, the product is always a compound, okay? While the reactants can either be elements or compounds. We have to remember that it's always the product, okay, that is always a compound. Let's take a look at some examples. We have here zinc plus sulfur, which will produce zinc sulfide. As you can see here, we are going to go back to the equation that we written a while ago. Simply A plus B will produce AB. Wherein A is zinc and B is sulfur, and it will produce zinc sulfide. Shown on the screen are pictures of the reaction. Sulfur is in a powder form, and then zinc is in the form of a hot nail. So upon dropping the hot nail in the powder form, it will produce this smoke, okay, indicating that there is a chemical reaction that occurred. Take a look at another example. We have here aluminum plus iodine, which will produce aluminum iodide. As you can see in the reaction, it produces heat and light. There is also existence of smoke or the production of gas. Again, this is an example of a combination reaction wherein A plus B will produce AB. Simply a combination or bonding of the reactants. And then mentioned a while ago that product is always a compound in a combination reaction, but that does not mean that the reactant should always be an element. Reactants can also be a compound, just like what we see in this example. So we have sulfur trioxide plus water will produce sulfuric acid. Okay, so we have here a compound. So we have here a compound A plus B will produce AB. As you can see, compound sulfur trioxide and the compound H2O or water will still produce a compound which is our sulfuric acid. So it does not necessarily mean that reactants should only be elements. Okay? They can either be element or a compound. But if we're talking about the product, it should always be a compound. Let's take a look at this example. We have here Na or sodium. We have chlorine, and then we also have NaCl. So upon adding sodium, which is in form of a soft metal, and chlorine, which is in form of a yellowish gas, it will produce NaCl or what we call the table salt. This is another example of a combination reaction wherein, again, A plus B will produce AB. A simple combination of the both. Hopefully, combination reaction is clear. Let's proceed with our next chemical reaction, which is decomposition. Decomposition is wherein a single compound breaks into two or more substances. Let's write it in a formula format. It says here a single compound breaks into two or more simple substances. So we have a compound, and the AB breaks into two or more simple substances will produce A plus B. So if you were to observe it and compare it with the combination reaction and decomposition are opposites. If in the combination reaction you are combining them together, in this one you are breaking them apart. Okay? We have here a compound that will break into two or more simpler substances, which is A and B. In this one, reactant is always a compound. And we have to remember that one reactant in the composition reaction is always a reactant, opposite of that of the combination reaction, wherein the product is always the compound. In this one, it's always the reactant. Let's take a look at our examples. We have here mercury oxide will turn into mercury and oxygen. So how is this observable? So as you can see, we have here powdered form the mercury oxide, which is subjected into heat. Okay, that helps the decomposition of our compound. If you are writing in a chemical equation form and it involves the use of heat, kindly put triangle on top of our arrow to indicate that it the compound was heated to produce a chemical reaction. So again, upon heating our compound, it produced two simpler substances, okay, which is mercury and oxygen. Take a look at another one. We have here potassium chlorate will produce potassium chloride and oxygen. In here, as you can see, we use heat to induce and to decompose our potassium chlorate. So for this one, we have to add again a triangle on the arrow to indicate that we used heat to produce a chemical reaction. So if you are to go back to our equation a while ago, we have AB will produce A plus B. As you can see, our reactant is a compound. Remember that in a decomposition reaction, our reactant is always a compound. It's the opposite of the combination reaction. Let's proceed with our next one. Single replacement, or it is also known as single displacement. This is wherein an atom or a molecule replaces an atom from a compound. So how does it look like? If you are to put it in a formula form, we have here A plus BX will produce AX plus B. Okay, and then as you can see here, BX is a compound, A can be an element. So combining these two will produce AX plus B. If you observe, the partner of X switched. Okay, in the reactant side, the partner of X is B. In the product side, the partner of X became A. This is what we call the single replacement. We are replacing another atom. Okay, we are replacing another atom in a compound. How do we know which one is being replaced? We follow the activity of metals. What is the activity of metals? Activity series of metals, hydrogen, and nonmetals are shown in the screen. As you can see, we have listed here different types of elements, and you can see these labels wherein we have the most reactive and the least reactive. The name says it for itself. Going to the right, okay, elements have less and less reactivity. Let's say, for example, if we are to compare gold between lithium, lithium is the most reactive, while gold is the least reactive. Okay, why is it important in single replacement? Most reactive elements or more reactive elements can replace the least or lesser reactive ones. Let's take a look at one example for us to understand it. We have here iron plus copper sulfate, and it will produce copper plus iron sulfate. Okay, as you can see, iron and copper interchange their places. Okay, now why does that happen? Let's take a look at our activity series of metals. Let's take a look at iron here and take a look at copper. Okay, as mentioned a while ago, more reactive elements can replace the lesser reactive ones. So since in our reactive side, sulfate is attached or is bonded with copper, upon interacting with iron, since iron is more reactive than copper, it can replace copper in the compound. Okay? Thus making it an iron sulfate. Again, lesser reactive elements will be replaced by more reactive ones. Take a look at other examples. Next, we have magnesium plus nickel nitrate. Despite magnesium in our reactivity series, so we have here magnesium and we have here nickel. Okay? Since magnesium is much reactive than nickel, our product now will be nickel. Okay, our product now will be nickel plus magnesium nitrate. Lesser reactive elements will be replaced by a more reactive element. Try to find the product for our next reactants. We have here zinc plus copper sulfate. What do you think will be our product? Let's take a look at our reactivity series of metals. So we have here zinc, which is located here. And we have our copper, which is this one. Looking at the two, zinc is more reactive, so it can replace copper as being bonded with sulfate. So our product now will be copper and zinc sulfate. Okay, let's try the next one. We have here nickel plus iron sulfate. Try to look for the possible product of this reactants. For this one, let's take a look at our elements. So for the elements, we have again iron and nickel. Okay, looking at it, the one bonded with our sulfate is the iron, which is much more reactive than nickel. This means that there will be no change in this reactant, so there will be no reaction. Okay, since nickel is much less reactive than our iron, it cannot replace it in our compound, so there will be no reaction. Hopefully, you're following through with our discussion about single replacement. Let's proceed with double replacement. Double replacement now is wherein two substances exchange parts with one another and form two different substances. What is the formula for this one? It's AX plus BY will produce AY plus BX. Okay? And then as you can see, they interchange their partners. Okay? AX become AY, BY become BX. Okay? Two substances exchanging parts with one another and forming two different substances. We have to remember in double replacement that the product is either a precipitate and it can also be a gas and liquid. So there should always be a precipitate or a solid particle in this one. Let's take a look at our examples. So in our examples, we'll be taking a look at our solubility table. This will be helpful in knowing which product is the precipitate and which is the gas or liquid. Potassium iodide and lead nitrate will produce potassium nitrate and lead iodide. With this product, let's take a look at which is the precipitate and which is the gas or liquid. So let's see here. First product is potassium nitrate. So let's take a look at potassium and we have the nitrate. Okay, you simply look for their intersection. Combining the two elements produces a soluble solution. This is not our precipitate. How about lead iodide? So we have here lead and iodine. So combining the two produces an insoluble product. So this one will be our precipitate and this one is our liquid. Okay, let's take a look at this picture for us to see what is the product when you combine these two reactants. Okay, as you can see, potassium iodide and lead nitrate are both clear solutions or clear compounds. And then upon adding them with each other, they will be producing a yellow precipitate. Okay, let's take a look at our next one. We have here silver nitrate plus salt, which will produce silver chloride and sodium nitrate. Let's figure out which of the two is our insoluble product or our precipitate. So let's take a look at for silver. And then our chlorine, which is here. And then take a look at their intersection. And then as we can see, it's insoluble. So our silver chloride will be our precipitate. Okay. How about sodium nitrate? So we have here sodium and the nitrate, and both of these are soluble with each other. Okay, let's take a look at the picture of the products. Then as you can see, upon dropping our silver nitrate, it produced upon dropping the reactant, okay, it produced a white cloudy precipitate, which is our silver chloride. Okay, let's proceed with the last type of chemical reaction, and this is the most common chemical reaction that we can observe. We have the combustion reaction. In this reaction, there is a reaction between a substance and oxygen that evolves to heat and light. Involved in this one usually are also hydrocarbons. So what is the formula for combustion? So for combustion, we have CX plus HY will produce carbon dioxide and water. Okay? So we have here our reactants and they usually produce carbon dioxide and water. Sometimes carbon dioxide is replaced by other toxic gases. We'll take a look at them later on with our examples. But let's take a look at this example first. As I've mentioned, combustion reaction usually involves hydrocarbons. So first, let's have an example which is CH4 or methane plus oxygen. Methane plus oxygen will produce carbon dioxide and water. Okay, this is a combustion reaction. Again, this carbon dioxide and water is observable by the production of heat and light, or the production of fire. Let's take a look at some of our examples. So we have here 2 hydrogen sulfide plus oxygen will produce sulfur dioxide and water. Mentioned a while ago that usually a product of a combustion reaction is carbon dioxide and water, but sometimes carbon dioxide is replaced by another toxic gas. So in this one, our toxic gas is sulfur dioxide. Another reaction is ammonia and oxygen, which will produce nitric oxide, which is another harmful gas or a toxic gas, and water. These are just some of the examples of a combustion reaction that instead of producing carbon dioxide, they produce another type of a toxic gas. Let's have a quick review of the different types of chemical reactions. So first we have the combustion reaction wherein A plus B will produce AB. Again, the products in this one are always a compound. Okay? Decomposition reaction, on the other hand, is the opposite, wherein we have AB will produce A plus B. In this one, the reactants are always the compound. Okay? Single replacement, on the other hand, is A plus BX will produce AX plus B. In this one, we follow the activity series of metals. Again, if it's more reactive element, it can replace the less reactive one. Double displacement, on the other hand, is AX plus BY, which will produce AY plus BX. This is what we also call the partner switching, okay, wherein it can produce a solid precipitate. And the most common and our last type of chemical reaction, which is the combustion, it's CX plus HY will produce water and carbon dioxide or a toxic gas. So kindly take note of the differences of these 5 chemical reactions because you can observe them in your laboratory activity. Let's now proceed with the discussion about solutions. First, let's define what solutions are. Solutions are a homogeneous mixture of 2 or more substances with each substance retaining its own chemical identity. So we have here an example shown on the screen, solution of water and salt. These are the substances that we are referring to. What we have here is a homogeneous mixture. So when we say a homogeneous mixture, it means that the substance that we are observing has a uniform appearance. You cannot distinguish anymore which the components are and they do not settle over time. Solutions have 2 components. We have what we call first the solvent. This is the component that is present in the greatest amount. This is also the medium that does the dissolving of the solute. So let's say, for example, in a salt solution, we have here water as our solvent. It is the one that is in much greater amount and it dissolves our solute. Solute, on the other hand, is the component that is present in a relatively lesser amount than compared to the solvent. It is the substance that is subjected to be dissolved. Going back to our example, the salt here is the one that is being dissolved, which makes it the solute. So we have here mixing solute, which is our salt, and mixing it with water, which is our solvent. Dissolving it will produce salt solution. And as you can see, the substance has a uniform appearance. You cannot see the salt particles anymore. Now, there are three different types of solutions. We have the saturated, the supersaturated, and the unsaturated solution. Let's define them one by one. First, we have the unsaturated solution. This means that the solution contains less than the maximum amount of solute that can be dissolved in a solution. So let's try to visualize it. Let's say, for example, you have here your salt solution. So our solvent here will be water, and our solute will be salt. Let's say, for example, inside this beaker, we have 200 ml water. Okay? In a 200 ml water, we can dissolve 36 milligrams of salt. In our saturated solution, we have, let's say, for example, 24 milligrams of solution. Looking at this amount, can our solvent dissolve our solute? Yes. Okay. Again, in an unsaturated solution, it contains less than the maximum amount of solute that can be dissolved in a solution. Okay. This is what unsaturated is. We have lesser amount of solute. Next, we have the saturated solution. Saturated solution means there is a maximum amount of solute that can be dissolved under the conditions at which the solution exists. So let's say, for example, in this one, we still have our 200 ml of water, and then we have salt, which has 40 milligrams. Okay? In this one, we have the maximum amount of solute that can be dissolved in our solvent, which means that this solution cannot dissolve any more solute. Okay, it already reached the maximum amount of solvent. It already reached the maximum amount of solute that can be dissolved in a solvent, making it saturated. Okay, no more solute can be dissolved in this one. The next one is a supersaturated solution. It contains more dissolved solute than the present in a saturated solution. Okay? So if in a saturated solution we have 40 milligrams, in this one we have 60 milligrams of solute, meaning we have a lot of solute to dissolve. Okay? But again, because the 200 ml of water can only dissolve 36 milligrams of solute, this means that there could be crystals forming at the bottom of our container. Okay, let's take a look at our picture or diagram for us to understand it much further. As you can see here, shown in this is the visualization of the three types of solution. So we have the unsaturated, where as you can see, more solute dissolves because it only has less solute. In the saturated one, okay, no more solute can dissolve, okay, because it already reached the maximum amount. In a supersaturated, on the other hand, crystals may grow, as mentioned a while ago, because of the excess solute that it has, okay, and the solvent cannot dissolve further. Crystals can grow at the bottom of our solution. This is the difference between the three types of solution. Next, let's discuss the properties of a solution. So we have solubility and miscibility. What is the difference between the two? Solubility versus miscibility. First, let's define what solubility is. Solubility is when you combine solid in a liquid, observing if the solute will dissolve in our solvent. So the solid one here will be our solute. Okay, and the liquid will be our solvent. In this example, we have the salt as our solute and we have water as our solvent. We also have these two concepts. We have soluble and insoluble. Soluble means that the solute dissolved, okay, in our solvent, just like what is shown in this picture. Insoluble, on the other hand, means it did not dissolve, okay? Soluble means that the solid in the liquid dissolved, while insoluble means that the solid in the liquid did not dissolve, okay? What is its difference with miscibility? Miscibility, on the other hand, is liquid in liquid. Kindly remember that in liquid, like dissolves like. That means polar can only dissolve or mix with a polar compound. Non-polar can only mix with a non-polar compound. Okay? So as you can see in this one, we have the oil and water. Okay? Liquid oil, liquid water. So like dissolves like. Since water is polar and oil is non-polar, they do not mix with each other. The terms that we use for miscibility is miscible, okay, and immiscible. By miscible meaning two liquids mixed with each other, while immiscible means did not mix. Okay, trying to remember that. Do not confuse miscible with soluble, insoluble, and immiscible. Solubility talks about solid and liquid. Okay, solid plus liquid. Miscibility is liquid plus liquid. Hoping we're already clear in this, let's proceed with our next part, which are the factors affecting the rate of solution formation. So we have here temperature, agitation, and particle size and surface size. So this four factors, they can affect the rate at which a solution can be formed. So how can they affect them? Let's discuss them one by one. Starting with the first one, which is our temperature. So in temperature, we have difference if the solution is solid in liquids and if it's gas in liquids. Let's start first with solid in liquids. It is much harder for a solute to dissolve in a cold temperature. Okay? The higher the temperature is, the higher the solubility, meaning it's directly proportional. Let's say, for example, you are making coffee. Okay? It's much easier for your coffee powder, creamer, and sugar to dissolve in a hot water compared with an ice cold water. Okay? That's because the higher temperature, the higher the solubility is. So in solids and liquids, solubility, okay, solubility and temperature are directly proportional, meaning the higher the temperature, the higher the solubility is. If there is lower temperature, there is also low chance of solubility. Okay? Remember, this is only applicable in solid in liquids. How about gas in liquids? Gas in liquids, okay, can also be affected by the temperature. A high temperature means higher kinetic energy. With that high kinetic energy, there is a low chance of the components to interact. The components that we are talking here are the molecules of the solute and the molecules of the solvent. So that means the higher the temperature, the lower the solubility is. This is quite the opposite in solid in liquid. So in gas and liquids, the higher the temperature, the lower the solubility. Okay? Again, because high temperature indicates that there is high kinetic energy, there is a low chance for the components of both the solvent and the solute to interact with each other. Because of the higher temperature, okay, oxygen in water is not dissolved or is not mixed thoroughly with water, making it harder for the fish to be alive during this high temperature seasons. Let's proceed with the next one. Again, kindly remember, temperature in solid in liquids is directly proportional, while temperature in gas in liquids are inversely proportional. Okay? Next, we have agitation. Agitation, or what we call stirring. Okay? It increases the interaction between the solute and the solvent because you are constantly moving the mixture or the solution. You are also making the components interact with each other. So this is directly proportional. The more you stir, the faster you stir your solution, the higher the solubility is, the higher the chance that your solute will dissolve and will mix with your solvent. Next, we have particle size and surface area. If you have a smaller size of a solute and there is a greater surface area, then the higher the solubility is. Let's say, for example, you have a sugar cube and a crushed sugar cube or a granulated sugar, the one that we normally use in the kitchen. In the sugar cube, okay, if you are to drop it, it will take a longer time to dissolve. Okay, in comparison with the granulated sugar, which can dissolve in such a short time. Okay, that's because, okay, let's take a look at this one. Size to solubility rate is inversely proportional. That means the larger the size, okay, the slower, okay, or the lower its solubility rate is. Let's say, for example, in this sugar cube and granulated sugar. If you are to put sugar cube in a beaker of water, it will take a lot of time to dissolve, especially if you are not stirring it. But with the crushed sugar cube or the granulated sugar, because it has smaller size, okay, it can dissolve easily. It can easily be mixed with water. Okay, that's the size to rate relationship. Surface area, on the other hand, is directly proportional. That means the larger surface area, the faster it dissolves. Okay? Let's say, for example, in the sugar cube. In the sugar cube, the surface area that it can occupy in our beaker is only this area. Okay, making it a lot slower to dissolve. Okay, meaning the surface area that interacts with our solvent is only this area. On the other hand, since the granulated sugar, okay, is smaller, they have a larger surface area. They can cover the whole beaker. Okay? So the surfaces of these granules interact with our solvent. Okay? Again, we are talking about the surface area, which means the surface area combined of all of these granules is the one that we are referring to. So since this granulated sugar has more surface area than the sugar cube, they dissolve much faster because they interact with our solvent molecules much more often. Okay? So again, particle size is inversely proportional. Surface area is directly proportional. Okay? So those are the factors that affect the rate of solution formation. Next, let's proceed with the difference between the aqueous and non-aqueous solution. Aqueous solution is wherein the water is the solvent. Aqueous, okay, meaning water is the solvent. Non-aqueous solution, on the other hand, is when a substance other than water is the solvent. Let's say, for example, it's alcohol, okay, or another organic substance. Okay, again, aqueous is when water is the solvent. Non-aqueous is when substance other than water is the solvent. Let's take a quick look at our solubility rules. So here are some lists of the elements or compounds soluble in water and those that are not soluble in water. Familiarize yourself with this one because it may appear in your quizzes. Let's try to practice them with some of example compounds. So we have here sodium sulfate. Okay, let's try to see if this compound is soluble in water. So we have here sodium. Sodium is soluble in water, while sulfate or SO4 are also soluble in water. This means that this compound is soluble in water. Okay, let's try another one. We have here silver nitrate. Silver is an exemption in our number 4, that which is soluble in water. But nitrate, on the other hand, is soluble in water. Okay? Here are our nitrate ion. These are soluble in water. Thus, this makes our compound soluble in water. Okay? So familiarize yourself with some of the exemptions, okay, from the ions that are also involved. So that's it for our discussion for the pre-laboratory in Module 3. So let's just go back to our objectives. So during the discussion, we already differentiated the different types of chemical reaction, and we also observed some examples of the changes that occurred. You are also now familiarized with the properties of solutions and the different factors affecting the solubility. Should you have any questions with the module, kindly email me at my email, which is lozano.angelajoy@auf.edu.ph. Hopefully you understand our discussion for now. Please proceed with your module activity and your laboratory experiment. Thank you and God bless.